Hello and welcome to the 11th presentation in the Treesearch and WWSC Center virtual conference series. This conference series was initiated to contribute to the scientific discussion in a time where conferences are cancelled due to the COVID-19 pandemic. The full program and previous presentations can be found at the Treesearch webpage. My name is Josephine Legård, and today I have the pleasure to present today's speaker, Peter Olsén, who will present synthetic strategies for decorating biopolymers with rings. Peter is a researcher at KTH with a research focus on organic chemistry and polymer chemistry. You in the audience can interact and ask questions or comment via the YouTube chat function. And the questions will be answered after the presentation. That will approximately 30 minutes. And with that, I hand over to you, Peter. So I stop sharing my screen.
Thank you, Josephine. Just see here that the technology working. So that. So thank you so much for that nice introduction. So my name is Peter Olsén, and today I will talk about synthetic strategies for decorating biopolymers with rings. And the reason I have this Christmas tree here is that last week when I was doing the presentation, it was actually snowing outside. So I felt a bit inspired when I took the title name. Obviously, in this case, I will work on a very different length scale than a Christmas tree decoration, but the concepts are quite similar. So I work as a researcher in the biocomposites group of Lars Berglund. So this is a picture here before Christmas when we were all together at the outskirts of Stockholm discussing our future endeavors. So my interest is mainly on functionalization strategies and polymerization methodology development, and I'm really interested in the functionalization of biopolymers, inspired by some kind of sustainable chemistry and how we can utilize green chemistry approaches to foster our transformation. And I really like ring opening reactions in general and how we can use that for developing new polymerization system. So I tried to view my interests somewhere here in the borderline of organic chemistry, polymer chemistry, and material chemistry, mostly inspired by organic chemistry and polymer chemistry, and trying to solve interesting problem here at the interface, so to say. But before I continue with my presentation, I want to acknowledge my first supervisor, Professor Anselme Albertsson, for receiving the 2019 Anselme Payen Award that we were actually going to unfortunately we couldn't go to ACS to attend the symposium, but this would do instead. So when I started as a PhD student, Professor Anselme Albertsson had just received an ERC advanced grant. So we were 5 PhD students starting roughly at the same time, with the focus of creating a completely new material concept, where materials that were heterogeneous at the micro scale, but homogeneous at the macro scale, similar to how nature build its materials. And within that, one of my focus area was synthetic development of ring opening polymerization, monomer synthesis. And from that point on, the interest in opening rings were born, more or less. So the idea of this presentation, I will go over some general features of ring opening reaction and then try to connect that to modification of biopolymers. So as a polymer chemist, if we think about ring opening reactions, the first point that comes up is, of course, ring opening polymerization. We have this nucleophile reacting with heteroaromatic ring, and you have the release of the ring, and you have the propagation. Very, very, very important here is that this is an equilibrium reaction. And being an equilibrium reaction, it is dictated by the thermodynamics of the system. So this figure here at the left corner visualize these different lactone monomers and their polymerization behavior at standard conditions. And these standard conditions is at 1 mole concentration and at 25 degrees. And as you see here, all except the 5-membered ring are polymerizable at these conditions. However, if you really cool the system to say -40, you can actually achieve polymerization of this gamma butyrolactone as well. That was discovered now just, I think it's five years ago. Very, very interesting indeed. Along those lines, we wrote a perspective relating to ring opening polymerization and how you should think. And when you design these monomeric building block, what you can expect of the polymerization behavior. And if you understand the features of the system, how you can transition between monomeric form and polymeric form by just twisting the surrounding system. Along those lines, we also published a project relating to just this feature, where you start here at high concentration of the monomer and create a system where you convert it to the polymeric form. But after just switching the system, you actually go back to the monomeric form. So you start to have depolymerization from the chain end and reforming the monomer. In principle, through this, you create an indefinitely recyclable material system. So there was just some of the parts from my a very condensed PhD studies in a few minutes. So after that, I ventured to the Department of Organic Chemistry, working in the areas of homogeneous water oxidation catalysis and total synthesis of peptides. And in some weird way, even though I was immersed in a completely different area, I still continue to open rings. So in my mind, there's always a ring to the solution of a problem. So along those lines, I got really interested in the ability to open rings in water. And these are two of the main projects relating to that, where we wanted to create new type of linker molecules in the field of peptide science that we could cleave depending on how we wanted through an orthogonal stimulus. So we developed some concepts about how we can ring open cyclocarbonates with unprotected amino acids in water, and how we could use that as a way to create functional protecting group chemistry. So a very condensed background before entering into the work here at the WWSC. So for roughly 2 years ago, I started in the group of Lars Berglund as a postdoctoral researcher. And the discussion we had in the beginning was that I should roughly focus 50% on lignin and 50% on other stuff, which was perfect. And in my mind, I was thinking, now I will not try to work against ring opening reactions, but rather try to incorporate that directly. So from my perspective, I'm mostly been working in the molecular area, size area. So this is my very crude perspective on the buildup of wood. So you have the wood composed of plant cells, and then of course the plant cells is constructed in the cell wall. But here, as when we start having the biopolymeric structures with lignin, hemicellulose, and cellulose, this is the area where it, at least for me, is more understandable, where you can understand how you can use these macromolecules and do desired modification. So if I just think about these different structures in terms of chemical functionalization potential, you can think of just the lignin, where you have it decorated with phenolic groups, aliphatic alcohols, carboxylic acid, and alkenes. Hemicelluloses, you have aliphatic alcohols, some carboxylic acid, and in the case of cellulose, in the best case scenario, you can reach some aliphatic alcohols. If we translate this to some kind of stop sign concept, lignin is green, yellow, and red. So lignin is by far the easiest to do any type of chemical modification, due to the abundance of many different functional groups and that can be easier reached in this scenario. So we start with the project that relates to the combination of lignin and rings. And we are by far not the first ones in the world that attempt this, and they are example with combining lignin with epoxides, lactones, and the carbonates. I was very intrigued on combining lignin with caprolactone, mainly because this is such a good monomer. It can be polymerized in so many different systems. There are examples in the literature when they have done this. The first is from '94 with Glasser, catalyzed with stannous octate when they created these star-like copolymers, and also more recent example working with the newly developed organocatalytic systems, in this case TBD, as you can see here. So try to build something new. So looking at lignin, these are the function groups we will work with. We have the phenolics, aliphatic alcohol, carboxylic acids, and alkenes. And in this case, we have the OH group that can initiate for ring opening polymerization. So we thought very long and hard on how to address this problem. And obviously, we want to create materials that has a high lignin content, which means that we should design the branch in such a way that we have a functionality. We should also try to find a catalytic system that is sustainable and can work at the ambient temperature and hopefully be quite selective. Along those lines, we select the methan sulfonic acid as the catalytic system. So decorating lignin with rings. So the technical lignin we started with was the LignoBoost. It has a Mn of 2400 and a dispersity of 7.9. In the center, and by work by mainly Martin Lavocco, have focused a lot on the refining our technical lignins to a specific sustainable solvent fractionation cycles, going from ethyl acetate to ethanol to methanol to acetone. And through this, you create different fractions that are more defined in structure. But most important, if we want to do any type of synthetic manipulations afterwards, this creates fraction populations that are soluble in organic solvents, which of course is very beneficial. We did a very detailed characterization of these fractions in terms of its functional group distribution. We have the beta 04, beta 5, the still bean structures. What we could see is that the fractions are quite have the same functional group components, but in different compositions. So to really create these functional pre-polymers from lignin, we combined caprolactone with a OMEC, a monomer we developed during my PhD study. There's a functional carbonate monomer, and through that we can decorate these arms from the lignin core with different functions that can be later on used in various chemical approaches. So depending on the starting fraction we use, we create these different star copolymers. The graphical representation here is just based on the statistical average of the structure found in our fractions, and we use that. In this case, we have the ethanol fraction and the ethanol fraction and the ethyl acetate fraction, and we do silyene chemistry. What we could directly observe was very different material behavior, where one was more rigid and one was more soft. But of course, we went really in detail into what happened in the structure, and what it turns out is that the lignin backbone is not chemically inert, so when we do this modification of lignin, we really need to understand the interplay of how we're building our modification system. How is that changing the initial structure of the lignin backbone, and also what are the groups that are modified? So it requires a lot of detailed structural analysis, and the reason is we really need to connect these factors together in order to create the lignin with both lignin materials with both predictable and reproducible properties. So along those lines, one solution, these are just fresh data from the lab prior to the COVID-19 situation, where we made a synthetic green synthetic cascade going here from this is just lignoboost in water, and then we do a chemical modification, have the same lignoboost but chemically modified in water, where you can see we have made it completely water soluble. The tricky part here is obviously the analysis. As one person told me once, don't worry about synthesis, worry about characterization. And this is really the case when you work with lignin. The characterization parts take a long time. So that brings me on to the next topic, and that is about modifying fibers, in this case through ring opening polymerization. And so holocellulose fibers can be produced from more mild delignification with peracetic acid, and what it creates is a fiber that has a high hemicellulose content. And connect that back to the chemical possibilities offers. We have the hemicelluloses with aliphatic alcohols and carboxylic acid, and cellulose with aliphatic alcohols that we can modify here in this step. And our target modification in this case was to ring open and polymerize from the surface of the fibers. And there has been a lot of attention in the literature about these synthetic approach as well, working both with macrofibers and nanofibers. And a lot of work has been done by a new WWSC director, Eva Malmström, in this topic. So our approach here was more or less to try to understand how does the specific of the reaction system influence the outcome or the grafting outcome. So here, just looking at this is the classical representation. Looking here at the holocellulose fibers, we have caprolactone as the monomer, same catalytic system as we use for lignin, and then grafting out from the surface. Varying the reaction solvent where we perform this reaction, we had very different reaction outcome. As you can see here, just underneath conditions, here you look at the carbonyl peak that relates to the repeating unit of caprolactone. You can see a very small increase in intensity compared to the acetic acid system. And the obvious question here is, why do we observe these big differences? So when I was struggling with this problem in the lab, I performed, I think, 15 or 16 reaction in different solvent system. And when I was reading up on the literature, I found some very intriguing literature from the mid-70s by Gutmann about the empirical parameters for donor and acceptor properties of solvent. And this is a very important concept in the field of metallo-organic chemistry. However, I could not see any examples in the field of polymer science where they have used this. The reason why I really like these concepts is that you divide the properties of the solvents into two different components. You have the nucleophilic action of the solvent, and you have the electrophilic action of the solvent. And this is very neat, because then you can understand how this connects to the polymerization mechanism. So just plotting how the intensity of the carbonyl, which in a sense is the graft amount, correlates to the different solvent properties. I could see that we have a very strong correlation with the hydrogen bond donor strength of the reaction solvent, whereas the hydrogen bond acceptor strength, we have more or less no correlation. And the reason for this, we believe, is twofold. To have a high hydrogen bond donor strength value indicates that, and in this case, the polymerization mechanism is cationic ring opening polymerization that proceed to this cationic intermediate where you activate the monomer. Having a high hydrogen bond donor strength means that you can stabilize the transition state. And in this case, you will have the monomeric complex diffusing to the hydroxyls on the fiber structure to initiate polymerization, to start polymerization. But obviously, another very important factor is the actual swelling of the fiber structure that the solvent do in the system, and through that influence the amount of accessible OH group to initiate polymerization. So So the graft outcome in terms of weight increase was quite significant. In the case of acetic acid, we had a 40% weight increase compared to bulk conditions where we only had 2%. And this was also reflected in the thermal properties of the fiber, where in the case of acetic acid, we had very low moisture content, as you can see in this region, and very good, nice, and later thermal degradation temperature. But obviously, an interest is so we can see that we have more grafts depending on the solvent system. But an intriguing part is how is the graft structure? How is this distributed in the fibers? So by performing some NMR experiments, by just dispersing these fibers in chloroform, we could calculate the graft lengths on from our fiber structure. And what we can observe here is that when we use solvents, either bulk conditions, that is without solvents, or propylene carbonate as a solvent, we had very or much longer graft compared to acetic acid and DMSO, where you produced short graft. But if we compare that to in terms of density, in the acetic acid system, we had much higher concentrations of grafts. And if we looked at in terms of the moisture content, the equilibrium moisture content in the fiber, we can see here that we had created much more hydrophobic fibers with acetic acid as a system. So as an effect, using different solvent system when we perform this ring opening polymerization create completely different fibers. In the case of acetic acid, we have higher graft density, and the graft density is even that high that we believe that we have internal cell wall grafting as well. Whereas in the case of bulk or propylene carbonate or THF, we had a very unbeneficial reaction system with just short amount of grafts on the surface of the fibers. So in a sense, crudely speaking, the solvent will dictate the graft behavior, in this case, in the reaction system. But this was working on the big macrofibers. So Justin have made these very nice new type of CNFs based on hollow cellulose. So we wanted just to see if this concept is applicable on nanofibers as well. So what we did here, we just freeze-dyed the hollow CNF in water. We redispersed this in acetic acid, and then perform the ring opening polymerization in this case, and achieve a similar weight increase as in the macrofiber system. And the very beautiful thing in this system is that we could have modified CNF systems that are completely dispersible in chloroform, that you could actually solvent cast these and create some kind of transparent film with just BCL grafted CNFs. So then we go into some of the properties of these modified fibers. So my former supervisor is Professor Ann-Kristin Albertsson, and of course, being trained by her, I think a lot about the degradation behavior of our materials and what will be the end in a sense. What was very beautiful here with the different modification, and that brings us into the next project. Well, very beautiful here with the different modification strategies that we developed, where we either use no solvent at all or acetic acid, is that we could tailor the moisture content within the fiber. So a question we proposed along these lines was, does the residual moisture within the fibers create any form of degradation during processing? So in this case, we were looking at biocomposites formed by caprolactone modified fibers compounded together with PCl. So this was the concept. So you have caprolactone, polycaprolactone, and the good thing here is a very low melting temperature, can be processed at low temperature. Then we need to have some kind of degradation assessment, either by NMR or by NMR and SEC, and then see how long can we reuse this, and at what time is the degradation too significant to end of use and reuse the fibers in a sense. So if we connect these, so the question here is what is actually happening with the degraded matrix polymer during compounding and its relationship to the initial moisture content in the fiber. So when we do a polymer analysis, the two main methodologies we use is either SEC, size exclusion chromatography, looking at the distribution, the molecular weight distribution of the polymer phase, or we go to NMR, looking at the end group concentration in relationship to the repeating unit. These are two very powerful techniques that gives very different intel of the polymer population. So we wanted to see here, in a sense, are they the same? They should correlate before and after compounding. What is very intriguing here is that if we look at the molecular weight we observed by NMR, we can see a vast degradation of the polymer phase during compounding, and it has a close relationship with the initial moisture content in the fiber. However, if we look at the SEC values, we have more or less no changes in the main peak in the system. Whereas if we look here at the longer retention times that relates to shorter structure, we actually have the formation of shorter oligomers. So this was a very intriguing observation, which means that we have actually perhaps we have a degradation pathway that we have not really recognized within these materials that occur during compounding. So in a sense, what we have in this material, we can have three different scenarios happening in the material when we process this. Either we have no degradation of the matrix phase, which means that the change from SEC and the change from NMR will be the same, will be equal to 0. However, we can also have a homogeneous degradation pathway, where it means that during compound, throughout the entire material, we have a degradation, which means that these factors should still be the same, but they should be different from 0. However, if we have a pathway of degradation that is heterogeneous, just occurring at some small location in the material, this situation should hold true, that the difference, that they are different from each other. And if we plot these scenarios with our different materials we have formed here, from either here is bulk grafted in acetic acid with a low moisture content, and this is bulk grafted. We can see here that in the fibers that have a high initial moisture content, we have a severe heterogeneous degradation, which means that when we start the compounding, the water molecules diffuse out from the fibers and start to degrade the matrix at the interface, whereas this doesn't happen if we have a very successful grafting outcome. And this could either be good or bad. That all depends. What it could offer is a way to tailor the degradation of your materials by the modification of the fiber structure. So in a sense here, fiber structure. We also analyze some of the material properties. So these are just submitted manuscript, where we wanted to see how does the graft structure really influence the mechanical properties of the final biocomposite material, using the same amount of fibers, but just varying the graft structure from the fibers. So connecting back to what we have done before, we have the system either working at bulk conditions to do the chemical modification, or we're using acetic acid as the co-solvent during the chemical modification, creating two different populations of modified fibers, either one with very dense graft structure of the fiber surface and within the cell wall, and one where we have mostly long grafts on the outskirts of the fiber. And then we analyze the mechanical performance. And as we can see here, that even though we used the exact same amount of fibers, we had very, very different mechanical properties of our materials. We have a young modulus and strength of PCl was improved with almost 60%, and the toughness was improved 67%, using the same amount of fibers in this case. Our interpretation of this is twofold. For sure, if we have a more dense graft structure on the fiber, and an increased hydrophobic behavior, we will have better compatibility. But also, we observed a more significant nanofibrillation during compounding of these densely grafted fibers, and probably relating to the grafting within the cell wall. So in a sense, it's really important to really decipher how has the reaction occurred and to what extent, and how can we use that to tailor our properties. So just some concluding thoughts about modifying biopolymers with rings. So when I started this, I had a very simplistic pictures on how we should make this. Just look at the units, look at the function groups, and then just modify it. But as it turns out, reality is much more complex, and we really need to consider the whole buildup of the fiber structure. How is the solvent influence the swelling? How is the swelling influence the accessibility? And also connect that. How is this relating to the modification mechanism? And how can we create stable system where we can really tune and tailor these modification? And obviously, we need to be very thorough and understand that the reaction has happened in the way that we ought it to happen. And with that, I just want to acknowledge my PhD group, my first postdoc group, and my current biocomposite groups for all the help and input, and obviously all of you for listening to my presentation. Thank you for your attention.
Thank you so much, Peter, for this nice presentation. And now we open for questions from the audience. So please type in your questions in the chat. Peter, it's not often that you hear the combination lignin and the easiest.
Yeah, no.
But it was nice to hear that combination.
But not easy to understand what was happening afterwards. So it's
while we're waiting for questions, I take the opportunity to show the next upcoming presentation in this series, and it will be next Tuesday, when there's Professor Monica Ek from KTH who will present the bulk biorefinery, and it was, as usual, on Tuesdays we start at 10:15. And after that, we have one final presentation in this series, this Treesearch and WWSC Center virtual conference series that will end in May, but all presentations will be available on YouTube. So let's see if we have any questions. Yes, we have a question here. We have from Jakob Redlingeporn. So thank you, Peter, for your talk and sharing your fascination. Ring opening in water. Are there also enzymatic catalyzed strategies, or is this graft purely human artisan work?
So the strategies I looked at was purely synthetic strategies for achieving these transformations in water. No. Do you? But they are probably would be possible.
Can you repeat? Can you repeat that? I had some.
You have problem with connection.
Yes, I have some.
So in my work was purely relating to synthetic system development. But there were probably there exist enzymatic pathways you can use as well for this. So in this system, what you need to create is a nucleophile that is stronger than water. So you have to remove that competing reaction from the system, and through that you can selectively direct your reaction. in that manner. In this case, this was an amine nucleophile. That amines are more nucleophilic than water or alcohols in this system, and that's why we had this preferential reaction behavior.
Jakob also has follow-up. Also, graft on hemicellulose, not cellulose, indicated in the figure in Young et al. The graft highly selective on hemicellulose on OH groups, hydroxyl groups. Why and how? And how to get it on cellulose?
So in this case, we think that the hemicellulose play a crucial part, and that is mostly related to swelling and accessibility of the OH group on the hemicellulose compared to cellulose. Of course, we need more data to really pinpoint that, but that is at least our hypothesis at this point. If we want to direct it more to cellulose, then you need to create a reaction system that also activates the OH groups on the cellulose. So that could be to have a semi-solvated system, perhaps with an ionic liquid. That could be one way to achieve similar modification.
So there's still time to ask Peter some questions. I think it was really inspiring to see also how you think about the whole life cycle, so to say, of a potential material, and that could be inspiring for others who are working too.
Oh, that's nice. No.
So if there are no further questions, so I once again say thank you, Peter, for your nice presentation. Oh, and Jakob just says, cool. Thank you, Peter. Truly fascinating. So with no further questions or comments, so I say thank you to you, Peter, again, and thank you for all who were listening in the audience.
Thanks for being part of this.
Sådär.
Sådär. Då var